Okay, now we're moving on to Unit 8, which is energy. Here in Unit 8, you'll want to find PS21 and PS22. We'll begin with some of the formulas. Remember, this is designed for the person who does not want to use their formula sheet. Some basics: kinetic energy's equation. Kinetic energy is 1/2 mv squared. Energy is a scalar, by the way. So is work. Potential energy is mgh, mass times gravity times height. Work, force times distance. Power, work over time. Power is measured in watts. Work is in joules, and so is energy. And you can see there's some relationship here between those. Heat measured in calories, which has a relationship to joules. We'll see that relationship show up in one of these examples, I think. M times SH times delta T, that's the way the heat equation works. Work equals a change in energy, but it also equals force times distance. So you can see here's the work-energy relationship. So they're almost the same thing. They're the same units. They're both scalar quantities, but they're not the same. They have different definitions. Work is force times distance. And energy is the ability of an object to cause a change in the system or surroundings. Specific heat, the units for specific heat are calories per gram degrees Celsius. Every substance has a different specific heat. It's how much heat it can hold. The specific heat of water is what all other things are based on, and it's just 1 calorie per gram degrees Celsius. So the units for work and energy are joules, which is a Newton meter, which is a kilogram times a meter squared over a second squared. And power is measured in a watt, and watt is joules per second. That's a little review for the, if you're using your formula sheet, of course you'd want to write down all these units and stuff on the back of it. That'd be something you could do. Remember, no example problems, no numbers on the back of your formula sheets. Let's take a look here now at the auto problem. So once again, we've got to begin with the force diagram. Let's kind of go through here and break down our forces. So we have a 500 kilogram auto, and this is going to have a number of forces on it. One is weight, another is normal force. Then we have a person who's pushing at an angle. That means it has an X component and a Y component. So all that is one force called FP, FPY, FPX. It's got its components. And friction helps us stop this car. Given information, it tells you how rough the surface is. It's got a μ_k of 0.2. And then other information is a distance of 15. And from all this information, we can solve this. Now we can always do it the old way. So we can figure out what all these forces are. And then once we've figured out all the forces, we can kind of use those to find the difference or do a summation, and then we can use magic physics formulas and we can figure out our answer, which is how fast it's going after we try to stop it. I guess we're trying to start it here. So we can solve for the acceleration as we stop it, and then what the velocity was when we jumped in front of it. So this is what we'd like to solve for, V0, whatever that may be. So let's figure out these forces. So we have 500 times 9.8, so we're looking at 4,900 for the weight. That makes normal force isn't identical because we're pushing down at an angle. So let's deal with that now. So we have an angle of 20. We have a push of 20. So if you make sure you're in degree mode, you can go through and do 50 cosine 20. 50 cosine 20 can give you your x component. So most of it's in the x, 46.98. Basically all of it, 46.98, and then because of the 20 degree, we have a little bit of y component, 50 sine of 20. It gives me 17 for the y, so I put it in like that, 50 sine 20, I got 17. 17 is in here. That means the normal force is going to have the 17.1 added to it, so my Fn will be 4,900 plus the y component. The reason we need to know that is so we can calculate how much friction is involved or how much it helps us stop the car. So I get that number going up. Now it's time to do an equation. So to find the friction, we're going to do what we always do for friction, UK times the normal force. My normal force is 4917.1. The roughness is 0.2. So we just multiply those two things together, 0.2 times the normal force. Remember, it's greater than the weight this time because we push down, therefore increasing the friction as well as the normal force. 983.4 is what you get for FFK. So now we can kind of come up with our net force. So the net force being FFK plus the FPX, not FP but FPX. And remember, almost all of it was there, 46.98 was how much FPX we had. And then we also had our friction force, which we just found. You know, friction is doing more than we are to stop this vehicle. I think it was 0.4. So if we add those two things together, I still have my friction force in here, and I have this, so we just add 46.98 to that. We get 1030.4. So the net force was 1030.4. That's in newtons. So force is, it's as simple as this, guys. F equals ma, Newton's second law. So I put in 1030.4. I put in the mass. The mass was quite large, 500, and then we can solve for the acceleration. So we do that. We take the 1030.4 and we divide by 500, and we get an acceleration of 2.06. 2.06. Oops, 2.06 meters per second squared. And we can plug that into one of our magic physics formulas to figure out how fast it was going when we jumped in front of it. So magic physics formula number 4 is the one we want to use because it has distance in it, and we pushed it for a certain distance. The distance we pushed it for was 15. Started at 0, went to 15, so 15 minus 0, 2 times 2.06, plus how it started, and then where it finished up, so v naught squared and v. Well, if we're successful in stopping it, that would be 0, and we can solve for what that would be. Oh, by the way, that acceleration that we found is negative, because it was a stopping acceleration. So I neglected to mention that, but that's negative. That could really mess you up if your signs are wrong. 2 times negative 2.06 times 15 ends up with a negative sign, but that's okay because v naught is on the same side. So when we bring v naught over to the other side, we can switch the sign of the sum of all these things right here on the right side. So 2 times negative 2.06 times 15 is negative 61.8. Of course, when we bring v naught over, it makes it positive 61.8. And we just take the square root of each side, and that tells us what v naught is. So we get square root 61.8, not 0.08, 61.8, and we get 7.86 for how fast it was going when we jumped in front of it. And that's positive relative to the way that I set up my swirl. And we can get this answer again, and we can use a new method. So go back to our force diagram. And once again, it'd be useful to know what our net force was. And our net force was the push in the x. So the net force was 1030.4. So 1030.4 newtons, that was our net force. Now we can use this relationship, force times distance equals work. So if I put in 1030.4 and then the distance that it was pushed for was 15, we can get our work that way. And that's in joules, and it's a scalar quantity. It doesn't matter sign here in this example. So let me clear out our answer, 7.86. We're going to get that again here shortly if things work out like they should. Multiply by 15 the distance, we get 15,456. That'd be the net work in joules, 15,456. So work equals force times distance, but it also equals a change in the energy, and the energy changed in such a way that it was kinetic energy. So this 15,456 number in joules equals 1/2 mv squared minus 1/2 mv squared. Now remember that this comes to a point where it's at rest, so the final, which is over here, is going to be 0. Now we can exclude that negative sign because it's a scalar quantity. So we get 15,456. 15,456. That's going to be equal to 1/2 mv squared. That's the v naught we're after. So we take half of 500, which is 250. That equals v naught squared. That equals 15,456. 15,456 divided by 250 square root will tell us what v naught is. Divided by half the mass, square root it, and we get our velocity, 7.86 again. See how that works out? Checks out both ways. Good to know how to do it both ways and understand it too. So we'll go through and we'll fill this in now. We got all our information here. What do we have to do? Normal force. What was it? 4917.1. Work done by friction. You know, I didn't even calculate that. It wouldn't be so hard to do. 46.98. No, what was the friction force? I wish I wouldn't have crumpled all these up. Here's our friction force. 983.4, and we just multiply by the distance. Force times distance is work. So 983.4 times the distance, 15, gives me 14,751. The friction did 14,751. But remember, what we use to do it is we use the net. So it might be better to know what the net was if you're doing this. And that was 15,456. So I'll write that in over here. I think that's more important. That was the work net. Remember, there's also the push that we had involved in there. And we calculated the V naught both ways as 7.86. Alright, on to Sven-Oli. That took a while. On to Sven-Oli. So for the Sven-Oli problem, we're solving for specific heat of an unknown metal. So we're going to use the heat equation, MSH delta T. We're going to set it up twice. We're going to do a little transfer of heat. It says the mass of the metal was 100, so we'll put the metal on top. Mass of the water was 200. The final temperature of the water was 29. And the initial temperature of the water was 25. Wait, yeah, 25. Of course, the metal's 100 because it's boiling. And we can find our changes in there. Remember, the water has a specific heat of 1, and then these two things equal each other. So if we go 4 here and 61 here, 200 times 4 is 800. So 800 both ways. 800 divided by 100 divided by 61. That gives me my specific heat of 0.13. So Q 800.13 for specific heat. One more to go here in this first page of the study guide, and that's the hammer nail example. So the idea here is that work equals heat. Right, here's the concept. Work equals force times distance, which equals Q, which equals MSH delta T. So we begin by putting in our our force, 400. Put in our distance, 0.05, because it's got to be in meters. Newton meter gives you joule. 400 times 0.05 is 20. So we did 20 joules of work, and that equals the heat. So in Q equals MSH delta T, the specific heat kind of dictates how all the other units want to be, and it's 0.085 for the nail. And the nail has a mass of 3. And we put in our previous answer, heat 20 joules. That'll tell us our delta T in degrees Celsius. So all I got to do is say 20 divided by 3 divided by 0.085, and that gives me 78.4 for my temperature change. 78.4 goes in here. The work done was 20 joules. This is degrees C. That finishes the bottom of the first page. That's 18% of the exam right there, which was 15 minutes long.